Good morning, students. Chapter 4, Moving Charges and Magnetism. In last lecture, we have discussed about motion in magnetic field. Case 1, when charge Q enters magnetic field B with velocity V normally. Means when velocity and magnetic field, they are normal to each other, perpendicular to each other, then what is motion of charge particle? Yes, we know that charge will perform circular motion. That charge will perform circular motion. Yes, we know this. Okay, what is radius of circular motion? That equation we have obtained, R is equal to mv upon qb. So yes, when charge enters magnetic field normal to it will perform circular motion. Circular motion means like this. Yes, it is circular motion. It is circular motion. But now question is, when velocity is not normal to magnetic field, when velocity is not normal to magnetic field, then what happens? See, to understand this case, we will take one condition. See, that it is x-axis, for example. It is x-axis, for example. Okay. Yes, it is y-axis, and here it is z-axis. Clear about this? Okay. Let magnetic field is in this direction. Magnetic field is in this direction. Magnetic field is in this direction. Uniform magnetic field in this direction. Clear about this? So yes, magnetic field is in this direction. Okay. Now, if object enters this magnetic field, like this, with velocity v, charge plus q enters this magnetic field. Yes, in this region there is magnetic field. Okay, with velocity v. See, this magnetic field is parallel to x-axis. So I can say magnetic field is in x direction. Magnetic field is in x direction. Okay, to see from this figure it is clear that velocity and magnetic field, they are not perpendicular. There is angle between them, that is theta. That is angle between them, that it is theta. Clear about this? Okay, so here let charge particle enters magnetic field such that angle between V and B is theta. Okay, here charge Q enters magnetic field such that angle between V and B is theta. Means not normal. Then in such cases, what we have to do? See, we will resolve this velocity into components. One component in direction of B, magnetic field, another component perpendicular to magnetic field. See, again, we will resolve this velocity in two components. One in this direction, one in this direction, parallel to magnetic field, denoted by V parallel. Okay, and another perpendicular to magnetic field, that is V perpendicular. Clear about this? Again, we will resolve this V into components: parallel to magnetic field, perpendicular to magnetic field. So now we will try to see, resolve velocity in two components. First component, V parallel. It is parallel to magnetic field. It is parallel to magnetic field. Okay, and yes, from figure we can say this V parallel is equal to, this V parallel is equal to, it is V cos theta. Yes or no? Yes, it is. Yes, it is. Clear about this? Okay. Second component, V perpendicular. V perpendicular means this component which is perpendicular to magnetic field. Okay, that is perpendicular. It is perpendicular to magnetic field. It is perpendicular to magnetic field. And yes, from figure I can say this V perpendicular is equal to, it is V sin theta. Clear about this? Then yes, if velocity is not perpendicular to V, you have to resolve this V in two components, parallel to magnetic field and perpendicular to magnetic field. Clear about this? Okay. Now I will consider first component, that is V parallel. That is V parallel. Motion of charge due to V parallel component. See, what is equation of force? When charge moves in magnetic field, what is equation of force? We know that equation of force is F is equal to, it is Q V cross V. It is V cross V. And what is its magnitude? Yes, its magnitude is F is equal to, here it is Q V sin theta, where theta is angle between V and B. Theta is angle between V and B. See, motion of charge due to V parallel component. From figure, component of velocity V parallel and B, they are in same direction. They are in same direction. They are in same direction. See, V parallel and B, they are in same direction. So due to this V parallel component of velocity, force acting on a charge is zero. Why zero? Because V parallel and B, they are in same direction. V parallel is parallel to magnetic field. Yes or no? Is parallel to magnetic field. So therefore, force is equal to 0. Yes or no? Force is equal to 0. Now force is equal to 0, it means what? Force F is equal to 0. It means acceleration is equal to 0. It means velocity is constant. Velocity is constant. In this direction, what is velocity? V parallel. Then V parallel is constant. Means object is moving, particle is moving in x direction. In x direction. In this direction. In x direction with constant speed, V parallel. Clear about this? Again, motion of charge due to parallel component of velocity. Parallel component of velocity and magnetic field, they are in same direction. Same direction, then yes, you know, cross product will be 0. Then force is equal to 0. Force 0 means acceleration 0 means velocity constant. It means object is moving in this direction with constant velocity. V parallel. Clear? So what is one motion? One motion is particle is moving in x direction with constant velocity, with constant speed, V parallel. Now we will see effect of this perpendicular component. See, motion of charge due to V perpendicular component. Due to V perpendicular component. See, this magnetic field and this component. Magnetic field and this component, they are perpendicular, and yes, we know that when velocity is perpendicular to magnetic field, normal to magnetic field, it will perform circular motion. So yes, here V perpendicular is perpendicular to magnetic field, therefore charge will perform circular motion. It will perform circular motion with speed V perpendicular. Clear about this? Yes, in second case, this component of velocity is perpendicular to magnetic field. In case 1, last lecture we have discussed, when velocity is perpendicular to magnetic field, it will perform circular motion. It will perform circular motion. Clear about this? Clear about this? To see, due to parallel component, object is moving in x direction, forward direction. Due to perpendicular component, it is performing circular motion, and combination of such two motion is helical. What is difference between circular motion? If object performs motion like this, only this motion, it is called circular motion. But when object performs circular motion and moving in forward direction, then such motion is called helical motion. And helical motion is combination resultant of two individual motion. First, due to parallel component moving in forward direction, and second, due to perpendicular component which is circular motion. So clear about this? Due to parallel component, it will move in forward direction. Due to perpendicular component, it will perform circular motion. Then what is path of charge? See, path of charge will be like this. It will be helical. Clear? Yes, it is moving in forward direction. Also, it is performing circular motion. And what is resultant of this? Helical motion. It is called helical motion. So remember, students, when magnetic field and velocity, they are not normal to each other, means velocity has component parallel and perpendicular to magnetic field, it will perform helical motion. Okay, due to parallel component, it will move in forward direction. Due to perpendicular component, it will perform circular motion. So resultant of this is, okay, a particle will perform helical motion. Okay, what is its path? It is helical. Clear about this? Resultant due to these two components. Okay, now helical means it has some radius. Okay, see, each and every loop. If you take one spring, then what is the shape of that spring? Yes, it is helical. So what is radius of its helix? Okay, what is radius of helical path? See, what is radius of helical path? Here it is. It is performing circular motion due to which component of velocity? This perpendicular. Yes or no? Yes. Then it is performing circular motion due to perpendicular component of velocity. For circular motion, what is required? Centripetal force, that is mv square upon r. Yes or no? Yes. But here I will write V perpendicular. Why V perpendicular? Because due to this component it is performing circular motion. And yes, this side, what is magnetic force? It is QV perpendicular V. Clear about this? Then this cut. Then if I make R as subject, then R is equal to, yes, R is equal to it is M V perpendicular upon QV. So yes, it is difference between last case and this case. Clear about this? Then yes, how to find radius of helical path? R is equal to mv upon qv, but v you have to take perpendicular component of velocity, because when velocity is perpendicular to magnetic field, it will perform circular motion. Clear about this? Okay. Yes, next one is one terminology for this helical shape that you have to remember, and it is called pitch. Denoted by P. It is called pitch, denoted by P. What is pitch? Pitch is linear distance traveled during one revolution. linear distance traveled during one revolution. Linear distance traveled in one revolution. What is meaning of this? See in this figure. If it is starting from this point, yes, it is performing one revolution. Okay, or I can say if it is starting from this point, it is moving. Yes, again at this point. It is called one revolution. What is one revolution? Linear distance traveled in 1 second in one revolution is called pitch. So this distance, linear distance means this straight distance. It is called pitch. Okay, again, pitch means linear distance traveled in one revolution. It is called pitch. If you observe screw, okay, so what is linear distance between two threads? It is called pitch. If you have spring, then yes, linear distance between two successive turns is called pitch. So pitch means linear distance traveled in one revolution. Now how to find distance? Distance is equal to speed into time. Speed, linear distance, and it is traveling linear distance due to which component? Yes, due to parallel component. And speed into time. Linear distance traveling in one revolution, and in one revolution, what is time? It is called time period. It is denoted by capital T. So yes, it is equation of pitch. P is equal to V parallel into T. Clear about this? Okay, so yes, you have to remember this each and every equation. Clear about this? Case 2, when velocity is not normal to magnetic field, then path of charge will be helical. Helical is resultant of two individual motion, one in forward direction and one in circular. So its path will be helical. For helical path, what is equation of radius and what is equation of pitch, that you have to remember. Okay? Yes, in last two cases we have discussed motion of charge in only magnetic field. But if you are given charge particle in combined electric and magnetic field, then what happens? Motion in combined electric and magnetic field. And yes, first theory is velocity selector. Why it is named velocity selector? See, we will understand. Okay, let x-axis, y-axis, and here it is z-axis. Okay, let electric field is in y direction, magnetic field is in z direction, and charge is moving in this direction. Velocity, charge is moving plus q charge is moving in this direction. Clear about this? Again, x, y, z, perpendicular axis. In this region, electric field is in y direction, magnetic field is in z direction, and velocity is in x direction. Means they are mutually perpendicular to each other. See, electric field and magnetic field, they are perpendicular to each other. Electric field and magnetic field, they are perpendicular to each other, and such field is called cross field. It is called cross field. Clear about this? Now see, yes, we know that whenever charge is moving in electric and magnetic field, force is acting due to both. That is, force due to electric field, force due to magnetic field. Okay, how? Now we will understand. See, here, force acting on charge Q. F is equal to Fe, electric force, plus Fm, magnetic force. Yes, it is. F is equal to, what is equation? It is QE plus, what is equation of magnetic force? It is Q V cross V. Yes, here it is. Okay, again F is equal to, now see, we will take the direction. Here, QE, Q into E. So force acting on positive charge. Yes, we know that force acting on positive charge is in direction of electric field. It is positive charge. So due to electric field, force is acting on charge in this direction. In this direction, it is Fe. Force acting on this charge. Force acting on this charge due to electric field is in the direction of electric field, means in positive y direction. Then how to write? See, how to write? F is equal to QE. I can write Q. Charge, it is Q. Magnitude of electric field, it is E. And here see, this force is acting in y direction. What is unit vector in direction of y axis? J capital. Clear about this? Q as it is, electric field in y direction. Clear? Okay. Plus, here it is, plus. How to solve this? Q, V, B, sine 90. Yes or no? Yes, Q, V, B, sine 90. See, V and B, they are perpendicular to each other. So Q, V, B, sine 90. Now remember students, we know that A cross B is equal to AB sine theta n caret. AB sine theta n caret, where n caret is direction of their cross product. So what is direction of cross product of V cross B? How? Here, V is in this direction. Yes, it is z-axis on board. Actually, z-axis is perpendicular outside. Yes or no? Yes. It is x-axis, y-axis, z-axis is perpendicular to what? Coming outside. How to find direction of V cross B? Here, right hand, first of all in direction of V. Yes or no? Yes. Magnetic field is outside. Wrap your fingers outside. Thumb is in vertically downward direction. Yes or no? Again. Q, V cross V. First vector is V. Put your right hand in direction of V. Okay. B is perpendicular outside like this. Then thumb, it is in downward direction. Downward direction means negative y direction. And what is unit vector in negative y direction? It is minus j caret. It is minus j caret. Clear about this? Okay. So yes, here Fm, it is in this direction. Fm, magnetic force, it is in this direction. Okay. So yes, here how to write this? F is equal to Q E j caret minus Q V B j caret. Okay. Q V B j caret. Clear about this? So I can write this F is equal to Q E minus Q V B. Here it is J. Okay. See, force acting on charge due to electric field, force acting on charge due to magnetic field, they are in opposite direction. They are in opposite direction. Clear about this? Clear about this? Yes. Now if I consider value of electric field and magnetic field, if I select values of electric field and magnetic field such that force acting due to electric field and force acting due to magnetic field, their values become equal. So resultant force will become zero. Again, understand? Fe, yes, it is in upward direction. Fm, yes, it is in downward direction. If I select values of E and B such that their magnitudes are same, then yes, we can say if I select values of E and B such that Fe is equal to Fm, so therefore total force becomes 0. Total force becomes 0 because see, they are in opposite direction. If their magnitudes are same, then total force will become 0. Total force, what is its magnitude? It is QE. It is QE minus QVB is equal to 0. So therefore QE is equal to QVB. Okay, yes, Q cut. If you make V as subject, then V is equal to, it is E upon B. V is equal to, it is E upon B. Clear about this? But when, if I select values of E and B such that Fe is equal to Fn, magnitudes of these two forces are equal, then resultant force will become 0. Then QE minus QEB is equal to 0. And under such condition, V is equal to E upon B. Now, what is meaning of force? Students, again, what is meaning of force? Force is 0. Force is 0. It means acceleration is 0. And yes, velocity is constant. And velocity is constant. It means charge is moving undeflected. Charge is moving undeflected. It is moving undeflected. Clear about this? So yes, when magnetic field, electric field, they are perpendicular to each other, total force is equal to 0, means when V is equal to E upon B, then V is equal to E upon B. In this case, charge is moving undeflected. So what is use of this theory? Why it is named velocity selector? See here, understand. If I have one region, it is electric field, it is magnetic field. I have selected values of E and B. Now if I throw numbers of charges with different speeds, only charges having velocity V is equal to E upon B. Only charges having velocity V is equal to E upon B. They will move undeflected. Another charges will deflect. Again, if I have cross fields, electric field and magnetic field, I throw or I pass a beam of charges having different speeds, then only charges having speed V is equal to E upon B, they will move undeflected, means in same direction. Another charges with different speeds, they will be deflected. So clear about this? So yes, if I want some charge particles having value of velocity some fixed, then I have to set E and B such that I will get only those particles undeflected. So in such manner, we can say this cross field is used to select some charge particle with some specific speed. If we have numbers of charges moving in different speed, but I want charge with some specific speed, then I can use such cross field. Because in such cross field, only particles having speed V is equal to E upon B, they will move undeflected. So yes, it is use of this cross field to select charge particles with specific speed, that is V is equal to E upon B. That's why it is named velocity selector. Clear about this? So yes, you have to remember, and yes, you have to take care when you are dealing with direction. Clear about this? Right now.